Hey guys, so today we are going to be covering section 4.4, and that is called graphing with asymptotes. So all we're going to be doing in this one is learning how to determine where asymptotes are and then how to apply them when we are graphing different functions. All right. So if we're going to start talking about graphing with asymptotes, the first thing I think we should do is go over what are asymptotes. Well, consider this function. It's actually the function f of x is equal to 1 over x, in case you're curious. So if we look here, if you look on the right half plane, we can see the function is decreasing in that first quadrant, and it kind of just stays in that first quadrant. It doesn't really go anywhere else. But if we look here on the left-hand side of the plane, in the third quadrant, we can see the function is still decreasing everywhere, but it is kind of contained in this quadrant. So it seems like these axes right now are governing the behavior of the function. And in this case, it's actually not the axes, it's the asymptotes. First one we're going to look at is the vertical asymptote. It's this red line right here. It's a barrier that runs right down the middle. It is a vertical line. Notice that at no point does the function actually cross this line. This vertical asymptote behaves kind of like a bulkhead or a barrier or a dam. The function can get real close up into it and kind of run right alongside of it as you go off towards infinity. But it doesn't matter how close you get to it, you will never cross it. There's a discontinuity here. The function kind of has to hop over it. To be a vertical asymptote, the function can never actually cross it. It acts as a vertical barrier. This function is kind of stuck on either side. And what these vertical asymptotes do is kind of govern the behavior as this function goes up towards positive infinity and down towards negative infinity on the y-axis. This asymptote just kind of guides it up toward plus or minus infinity. But because due to the construction of these asymptotes, you can never actually cross this line. So that's what a vertical asymptote is. But if we're going to talk about a vertical asymptote, now it makes sense to talk about horizontal asymptotes. In this case, this horizontal asymptote is the line x is equal to 0, also known as the x-axis. You notice as you get closer towards negative infinity and positive infinity, these functions start to converge to the x-axis. They start to converge to this horizontal asymptote. So the way to think about horizontal asymptotes is it governs the trend of the function as you go towards plus or minus infinity in your inputs. So eventually, what does it converge to? Now, there is a very big difference between horizontal asymptotes and vertical asymptotes, besides the fact that one is straight up and down and one's lying flat. A horizontal asymptote is not quite as strong as a vertical asymptote. What I mean by that is a horizontal asymptote, you can actually jump. You can actually hop over it. In this case, the function doesn't. It stays governed down here. But there are cases where the function can kind of come up and actually cross the horizontal asymptote. The horizontal asymptote is not a barrier. It's not like that vertical asymptote where it's, you shall not pass kind of situation. The horizontal asymptote is more of a trend line. So it kind of dictates how the function is behaving as you get closer to plus or minus infinity, but it is not a strict barrier. So quickly recap that. The vertical asymptote is a vertical line that basically splits the function in two pieces that governs the function's behavior as it goes up towards plus or minus infinity on the y-axis. It kind of acts as a barrier. Think about a wave hitting a bulkhead. The wave comes crashing in and it hits that bulkhead and it shoots up it, but it doesn't actually cross the bulkhead, or at least not a good bulkhead. Now, with a horizontal asymptote, think trend line. How is this function behaving as we go towards plus or minus infinity? Kind of like a stock market prediction. And it kind of follows a certain curve. That's a trend line. But a horizontal asymptote is the function version of a trend line. What's it doing as you go towards plus infinity or minus infinity? But that kind of description is kind of intuitive. It's kind of geometric. We have to be looking at the graph in order to determine this. But this is college calculus. So what we're going to do is learn how to analytically analyze these functions. So basically determine where vertical asymptotes and horizontal asymptotes are without ever actually having to look at the graph. Why? Because we want these pieces of information to help us draw the graph. Now, we do not need these pieces of information if we already have the graph in hand. Does it kind of make sense? Oh, we need the picture of the graph in order to draw these things so we can draw the thing. Doesn't make any sense. So what we need to do is learn how to determine where the vertical and horizontal asymptotes are before we draw the function. Because actually knowing those pieces of information tacked on with all that other stuff we have in the previous 3 sections, we can come up with a pretty accurate sketch of what these functions look like. So let's move on to looking how to actually calculate vertical and horizontal asymptotes. For no rhyme or reason, first up to bat, we're going to go with vertical asymptotes. So this is the definition of vertical asymptote. A function f is said to have a vertical asymptote at x is equal to c if the limit as x approaches c from the left of f of x is plus or minus infinity, or the limit as x approaches c from the right of f of x is equal to plus or minus infinity. Now, first thing you see when you see a definition, well, let's think about what that means in terms of the intuitive knowledge we already have. So let's go look at this function again. Now notice as you tend in different directions, your function behaves differently. If you come at 0 from the right, you head up towards positive infinity, and you come at 0 from the left, you head towards negative infinity, and we have a vertical asymptote here. That is not a coincidence. That's what we define a vertical asymptote to be. But rather than just talking about it, let's actually look at these limit calculations. So we're talking about the limit as x approaches 0 from the right of 1 over x. We want to evaluate this limit. Now remember, the one-sided limits do not care what happens on the left side in this case. We do not care what happens to 0 on the left. It could not exist there for all we care. We only care in this case with how the function is behaving as we approach 0 from the right. So as we follow this function, as it gets closer and closer and closer to 0, what is its behavior? What is it doing? Well, notice we have 1 in the numerator and x in the denominator. Now we can't just plug in 0 because we cannot divide by 0. You cannot divide by 0. You just can't. Just can't. Not in the real numbers. It's not defined. But what we can do is remember what the limit process is. The limit is not actually plugging in numbers. You can only plug in if the function is continuous at that point. It's one of the nice things about continuity. But we kind of get lazy sometimes and just think about limits as just plugging in the value. If that was always true, then if we just are able to plug these numbers in for limits, the whole definition of the limit is kind of pointless, ain't it? So let's escape that mentality and remember what the limit process is. It is approach. What is this function doing as we get closer and closer and closer to 0 from the right-hand side? Well, let's think about that. When we start here at 1, when we plug in 1, that's just 1. This makes sense. But what about 1/2? Well, the function jumps up to 2. Now, what about 1/3? The function jumps up to 3. But what about at x is equal to 1/100th? Well, that means this function is going to equal to 100. It's going to be way up there past our screen. So if you notice, as we punch in smaller and smaller and smaller numbers into this denominator, this whole function is going to get huge. And that's actually a very important idea for us to think about. As we start punching in tiny numbers into the denominator, I mean tiny, we're getting close to 0 here, guys, like very small numbers. This whole function is going to blow up towards positive infinity. So think about that. Divide by small number, you get a bigger number. Divide by a tiny number, you get a really big number. Divide by a minute, minuscule, miniature little thing, and you're going to get an absolutely massive function value. So as that denominator gets smaller, the magnitude of the function gets bigger. But now you might be asking, how do we know it's positive infinity and not negative infinity? Well, that's because these values of 0 that we are plugging in are positive. We're coming up from 0 from the right. So we have a positive number in the numerator, and we're plugging in positive numbers in the denominator. So if both numbers are positive, then their ratio is always going to be positive. So while it's blowing up towards infinity, it's going towards positive infinity because all the numbers involved are positive. All right? So from that, we can conclude that the limit as x approaches 0 from the right of 1 over x is equal to infinity. Now, let's look at the limit as x approaches 0 from the left of 1 over x. Well, the same idea. As we punch in numbers right here that are getting closer and closer and closer to 0, so really small numbers in this denominator, the magnitude of this function is going to take off in an unbounded manner. It's going to get unboundedly big. It's going to get huge. The magnitude of it, that is. But since we're plugging in numbers that are just left of 0, those are negative numbers, that means we are dividing 1 by tiny negative numbers. So the fact that they're tiny means the magnitude of the function is going to get big. It's going to shoot off towards plus or minus infinity. But since the values we are plugging in are negative, we are actually converging towards negative infinity. So we can conclude here that this function has a vertical asymptote at x is equal to 0. At this point, x is equal to 0, we have a vertical asymptote, and this function kind of crashes into it at both sides. On the right side, it takes off towards positive infinity. The left side, it takes off towards negative infinity. So that gives us our vertical asymptote. And this is the technique or the kind of reasoning we're going to use when we calculate vertical asymptotes. All right? Well, let's see another example where we don't have a graph to reference. So consider this. The limit as x approaches 3 from the right of 4x minus 2 divided by x minus 3. So let's see what happens when we evaluate this limit. Now, we cannot just plug in 3. Why? Because if we plug in 3, then we get 3 minus 3 in the denominator, which is 0. We have 0 in the denominator, which cannot happen. We cannot divide by 0. So we cannot just plug in. We have to actually think about this. So we have the limit of a rational function. We have a numerator divided by a denominator. But by the properties of limits, what we can do is just take the limit of the top and we can take the limit of the bottom. Now, in the bottom we can't quite plug in because then we get a 0 in the denominator. But we can plug into the numerator because 4x minus 2 is continuous in the numerator. We don't care if it's equal to 0. So we get that the numerator is equal to 10. We just plugged in 3. And we get 10 divided by the limit as x approaches 3 from the right of x minus 3. So now we need to ask ourselves, what happens as we plug in values that get closer and closer and closer to 3? Well, 10 is fixed. The numerator is fixed. That's not going to affect anything. But as we start punching in numbers that are really close to 3, this denominator is going to get arbitrarily small. As we get arbitrarily closer to 3, their difference is going to be arbitrarily small. Like plug in 3.1 and then 3.001, 3.50 and then 1. You're going to get ridiculously close to 0. And as this denominator converges to 0, this whole thing, the magnitude of it is going to blow up. So as the denominator gets arbitrarily small, the whole thing gets arbitrarily big. So we converge to 3, the denominator is going to converge to 0, and then we're dividing 10 by really small numbers, which gives us an extraordinarily large magnitude in function. But the thing is, we're plugging in numbers as we approach 3 from the right. When we're talking about 3 from the right, we're talking about numbers that are just bigger than 3. So the denominator is going to get arbitrarily small, but it's going to get arbitrarily small with positive numbers. So we are dividing 10, a positive number, by arbitrarily small positive numbers. So that can tell us that this function is going to converge to plus infinity. Not negative infinity, plus infinity. As this denominator gets really, really small, the whole thing is going to get really big. So think of it like this. 10 divided by small is equal to big. But now, just because it's big, that doesn't mean it's positive or negative. Remember that. Big does not mean positive or negative. Big is referencing the magnitude. So if it's getting arbitrarily big, you know it's going to plus or minus infinity, but then we have to think about the sign of the numbers that we are plugging in. And in this case, 10, positive number. We're plugging in numbers that are just bigger than 3, so their difference are going to be positive. So you have a positive number divided by a positive number, which gives you infinity. So, quick example, if we are doing this from the left, x approaches 3 from the left, well, this whole thing is going to explode towards negative infinity. At home, I want you to try to work that out and see if you can work out the explanation for the limit as x approaches 3 from the left. All right? So this is kind of a strategy we are going to use, where we think about the sign of the numbers and what does the denominator in this case do to affect the whole thing. But notice, since the limit as x approaches 3 from the right of this function is equal to infinity, that tells us we have a vertical asymptote at x is equal to 3. Now, that's enough for vertical asymptotes. Let's look at horizontal asymptotes. We say f has a horizontal asymptote at y is equal to c if the limit as x approaches infinity of f of x is equal to c, or the limit as x approaches a negative infinity of f of x is equal to c. Notice the difference in definitions in these asymptotes. Before it was, is the limit as x approaches c from the left or right, this function takes off towards plus or minus infinity. But in this case, it's as we plug in bigger and bigger values of x, what does this function do? So that's the whole idea with horizontal asymptotes. As we punch in arbitrarily large values of x or arbitrarily negative values of x as we go towards plus or minus infinity, what happens to the function? Does it converge to a number, or does it take off toward plus or minus infinity? If it converges to a real number, a number we can hold, that means you have a horizontal asymptote at y is equal to that point. So let's see some examples. Suppose we want to find the vertical and horizontal asymptotes of f of x is equal to 1 divided by x minus 2. How are we going to do that? Well, first let's find the vertical asymptote. How do we find the vertical asymptotes? Well, we want to see if there is a value that as we take the limit as we approach it, does this function tend to plus or minus infinity? To find the vertical asymptote yourself, to try and play that guessing game, look at the function and see where it breaks. In this case, we have an x minus 2 in the denominator. So if we plug in x is equal to 2, it's actually going to have a division by 0. And this isn't going to be a whole here. There's no term in the numerator to cancel out the x minus 2. So when you have this x minus 2 in the denominator, we can kind of eyeball that and try and guess where the vertical asymptote is going to be. So what I'm going to do is I'm going to guess that the vertical asymptote is at x is equal to 2. Why? Because if we plug in 2, we have a 0 in the denominator. It's a pretty good place to start guessing to find a vertical asymptote. So let's check. Evaluate the limit as x approaches 2 from the right of 1 divided by x minus 2. Well, so we're going to be plugging in numbers that are going to get closer and closer and closer to 2 from the right. So they're bigger than 2, but they're getting arbitrarily close to it. It's converging to 2. So this denominator is going to get arbitrarily small. It's going to get ridiculously small, but they're all going to be positive numbers, and the numerator is positive. So we're going to have a big positive number divided by a tiny positive number, which tells us that this limit is going to converge to infinity. Remember, infinity is not a number. Infinity is a concept of unbounded magnitude. What that's telling us is this function is going to get arbitrarily big as we get closer and closer and closer to 2 from the right. It's going to take off towards plus infinity. But that's with the vertical asymptotes. We can conclude that f of x has a vertical asymptote at x is equal to 2. But now, what about horizontal asymptotes? Well, personally, I find the horizontal asymptotes a little bit easier because there is no guessing. The vertical asymptote, you kind of have to, it's a turkey shoot. You have to look at the function and try and ask yourself, okay, where would we might have a vertical asymptote? Where would this function run into a problem? With horizontal asymptotes, it's a little more straightforward. We just evaluate the limit as x approaches plus or minus infinity. And in this case, I'm just going to go with positive infinity. So take the limit as x approaches infinity of 1 over x minus 2. Ask ourselves what happens. Well, take x is equal to 10. Well, then this function is going to be 1/8. Right? But what happens if we plug in a billion? So we get 1 divided by a billion minus 2. That's a really big number in the denominator. And what happens when you take a fixed numerator and you divide it by an extraordinarily large denominator? So we have a small number being divided by a big number. Well, eventually that denominator is going to get so big that it's essentially going to eat up that numerator. And this whole thing is going to converge to 0. So this numerator right here, this 1 is fixed. But x is going to get extraordinarily big. Take the biggest number you can think of right now and then double it. We're talking numbers that big. And then take the biggest number you can think of and raise it to the biggest number you can think of's power. So not a Google times a Google, but a Google raised to Google. So a Google times itself a Google number of times. We're talking that kind of big number here. It's one of those kind of big numbers that makes your head hurt. And that's how big we're talking this denominator is going to get, to the point where the numerator is not even going to matter. It's going to destroy it in this case, because 1 is just a constant. It's not getting bigger with the denominator. It's fixed. So the denominator is going to dominate this fraction. So we can conclude that this limit as x approaches infinity is going to be equal to 0. So from there, this implies that we have a horizontal asymptote at y is equal to 0, also known as the x-axis. Another way to remember that is that if we have 1 divided by a really big number, it's going to be a small number. If you don't believe me, just play the calculator for a minute. Divide 1 by really big numbers and see what happens. It's going to start converging to 0. And that's what we mean by this function has a horizontal asymptote at y is equal to 0. All right, but that's in this case. The denominator does not always completely dominate. That is not always the case, otherwise this would be kind of dumb. It does not always converge to 0. It does not always converge to infinity. It's not one or the other. As we evaluate these limits to infinity, it might actually converge to a real number. So let's look at another example. All right, let's find the horizontal asymptotes of the function f of x is equal to 4x minus 2 divided by x minus 2. All right, well, we want to find the horizontal asymptotes, so that tells us we need to take the limit as x approaches infinity. So let's do that. Let's evaluate the limit as x approaches infinity of 4x minus 2 divided by x minus 2. Now, if we just want to try and quote-unquote plug in infinity, so a really big number, well, the numerator is going to go to infinity, and the denominator is going to go to infinity, and we're going to have infinity over infinity. Now, you might want to say infinity divided by infinity is equal to 1, but that is not necessarily true, because infinities are not numbers. We cannot divide them by each other. We cannot multiply infinity by infinity, not really. So to divide infinity by infinity doesn't make sense. They're not numbers. So we have to do a little bit of trickery here in order to get this in a situation that'll give us some useful information. Now notice, as we plug in x, as it gets larger and larger and larger, if you look in the numerator, this x right here, this 4x term, that's what's going to dominate the numerator. That negative 2, when we get big enough, is going to be irrelevant. Trillion minus 2 and is not really that different from a trillion. A Google minus 2 is still essentially a Google. It's minus 2. We really don't care. So this 4x here term here is going to dominate the numerator. And in this denominator, this x value right here, this is going to dominate the denominator, i.e., as we get bigger and bigger and bigger, this x value is going to overtake this negative 2, and this negative 2 is going to become irrelevant. So it's really these first two terms, these x's, that are going to dominate. Now, we're going to do something slightly strange. We're going to multiply by a very, very weird choice of 1, but just bear with me here. So we're going to multiply the numerator by 1 divided by x and the denominator by 1 divided by x. Since we're not plugging in 0, we're fine. We're talking about really big numbers. We don't care about it 0. So we're plugging in really big numbers, so we can multiply by 1 divided by x divided by 1 divided by x. 1 over x divided by 1 over x is just 1. Every time you plug in a number here that's big, it's going to be equal to 1. We're not changing the value, we're just changing the form. Now bear with me on as to why we did this. Because if we multiply this out, so take this 1 minus x and multiply it to both of these terms, take this 1 minus x and multiply both of these terms, we get this is equal to the limit as x approaches infinity of 4x divided by x minus 2 over x in the numerator, and in the denominator we get x divided by x minus 2 divided by x. I just multiplied every single term in the fraction by 1 over x. That's all we did. Now why did we do that? Well, notice in these terms there's an x in the numerator, x in the denominator, x in the numerator, x in the denominator. Since we're not divided by 0, these terms actually cancel with each other. So this limit can be rewritten as the limit as x approaches infinity of 4 minus 2 over x divided by 1 minus 2 over x. So all we did was multiply every term in the fraction by 1 over x, and then we canceled terms as we deem necessary. So we have 4 minus 2 over x divided by 1 minus 2 over x. These fractions are equivalent. They're equal to each other. This is the same thing. All we did was change the form without changing the value. Now, why did we do that? Well, let's take the limit. As we take the limit of the numerator and the denominator, we can pass the limit to all the terms. But 4 and 1 are constants. They're not changing. So those limits are going to stay the same. It's 4 and 1. But as we pass the limit to the numerator, it becomes 4 minus the limit of 2 divided by x. In the denominator, it becomes 1 minus the limit of 2 over x. So all I did now was pass these limit to all these terms. That's all we did. We haven't really done any calculus. We haven't done anything. We changed the form and rewrote the limit. That's it. Here is where the magic is going to happen. Let's look at this term right here. This limit as x approaches infinity of 2 divided by x. 2 is fixed, but this denominator, this x value, is going to get arbitrarily big. It's going to take off towards infinity. Now, what happens if we have a constant divided by a really big number? Well, this whole thing right here is going to converge to 0 because this x is going to eat up this 2. It's going to get so big this 2 is becoming irrelevant. And when we have a small number divided by an arbitrarily big number, it's going to converge to 0. And by the same logic, the limit as x approaches infinity of 2 divided by x in the denominator is also going to converge to 0. So when we actually calculate the limits, we get this is equal to 4 divided by 1, which is equal to 4. So we can conclude that we have a horizontal asymptote at y is equal to 4. Now, as a quick recap on what on earth we did, we recognized that there's an x value in the numerator and the denominator that are dominating these functions. And then when we took the limit as x approaches infinity of them, we want to kind of get rid of that x term right here. If we leave these x's in here, it's going to be infinity over infinity, which is going to be useless to us. So we multiply by 1 over x divided by 1 over x. Essentially, multiply every single term in the fraction by 1 over x. And then we cancel terms, pass the limit to all the terms, and then we recognize that these two limits right here are both going to go to 0 because you have a constant divided by an arbitrarily big number, which is going to go to 0, which is equal to 4 divided by 1, which is just equal to 4. All right, now let's look at another example. Let's say we want to find the limit as x approaches infinity of x squared plus 1 divided by x. Well, last time what we did was we recognized that the term x was dominating the whole function, so we divided every term by x. Now, here, we do have another x, but up here we have an x squared. And ask yourself, as we punch in bigger and bigger numbers, which is going to go towards infinity faster, x squared or x? Every number we plug in x is going to be big, but x squared is going to be 2 squared times bigger. So this x squared term is actually going to go to infinity faster. So when we do that trick we did last time, we don't want to use x this time. We want to use x squared. Why? Because x squared will go to 0 faster, or go to infinity faster than x. So let's see what happens when we divide every term by x squared. So we just multiply by 1 over x squared by 1 over x squared. This is just equal to 1, so we're changing the form, not the value. And then we distribute this to all the terms. This becomes the limit as x approaches infinity of x squared divided by x squared plus 1 over x squared divided by x squared. All we did was divide every single term in the fraction by x squared. So this notation is kind of funny. You might not really like seeing a fraction divided by another fraction, but all we're doing with this is dividing every single term in the fraction by x squared. Why do we want to do that? Because if we look here, those x squareds are going to cancel, and in here, one of those x's is going to cancel and leave us with the limit as x approaches infinity of 1 plus 1 over x squared divided by 1 over x. Where did the 1 come from? X squared divided by x squared is 1. We leave the 1 plus x squared alone, and then x divided by x squared Well, we can cancel an x in the numerator and x in the denominator and get 1 over x. Now that we're here, we might be asking, why on earth did we do that? This is why. Now we can pass the limit to all three of these terms. We can control them now. If we just left in this original form, this x squared plus 1 divided by x, it's going to get to infinity too quickly. We can't really see what's happening. But dividing by everything by x squared, we're kind of slowing it down a little bit, analytically speaking, so we can see what happens. This is going to converge to infinity. Why? Well, we pass this limit into this numerator. This 1 plus 1 over x squared is going to converge to 1. Why? Because 1 divided by x squared is going to converge to 0. Why again? Because the numerator is fixed at 1, and the denominator is going to get really big really fast. So this whole thing is going to converge to 0 as x goes to infinity. So we're left with a 1 in the numerator. But now let's look at the denominator. What happens as x gets arbitrarily big of 1 over x? Well, that means it's going to converge to 0. The limit as x approaches infinity of 1 over x is going to converge to 0 because that x is going to get really big. But what happens when you have a function that is kind of stagnant in the numerator and it's going to get arbitrarily small in the denominator? So we have a constant divided by an arbitrarily small number. That means the whole thing is going to get arbitrarily big, meaning this limit is equal to positive infinity. Just pass the limits of the numerator and the denominator. Ask yourselves what happens to all three terms. You'll get a 1 in the numerator. You're going to converge to 0 in the denominator. And when you start converging to 0 in the denominator, the whole thing is going to get arbitrarily big, resulting in this limit equaling infinity. What happens if the limit as x approaches infinity of this is equal to infinity? Well, that tells us that there is no horizontal asymptote, because as we get x arbitrarily big, it does not converge to a number. It skyrockets, it's off towards positive infinity. All right? Now, look at an example. You might be trying to wrap your head around why I chose x squared and not x like last time. Well, the next lecture, we're going to go over something called, or in the next part of this lecture, we're going to go over something called the Tower of Power, which is going to allow us kind of a way of picking what value we want to divide all these terms by. So when we take the limit as x goes to infinity, we actually get useful information. So that's it for this part of 4.1. Tune in next time and we will go over part 2 of section 4.4.